Okay, the goal of this video is to relate the rolling motion of a round object to translational motion. And so this could be for something like a bicycle wheel, a lawnmower wheel, an automobile wheel. We could be looking at a ball which is just rolling across the ground, or a tabletop, a marble, whatever. It doesn't really matter. The point is that there must be some way to relate the translational motion of the center of mass with the rolling motion of the object. And so that's our goal with this video. We're just going to try to help you better understand how we connect the two ideas, because they are connected. So we're going to start with looking at just a rotating disc. And the disc is just going to be spinning in place around the center point. The axis of rotation is just around the center point. Let's have it go in this direction just to give it a direction. So omega is going to be counterclockwise. And if we pick two locations, one which is right here, and the other one which is out towards the edge, then these two discs, or these 2 points on the disc, are going to be located at two different radii. So we'll just call this R1, and we'll call this one R2. Each of these are going to have to complete a circle in the same amount of time. So let's list out our facts. Both points complete one revolution in the same amount of time. The other fact is that both points, they must travel through two different distances. Okay, now the distance for each one is really just the circumference of the disk at the point at that particular radii. So, for R1, we've got a circle that looks like this, and then for R2 we have a much larger circle. Okay, and so it's very easy to see that each one is going to travel through a different distance. So in order for these two conditions to be true, that's going to imply that each point on the disk, each of those 2 points, has a different tangential velocity. Now, if you want to calculate the tangential velocity, we're just going to say that V1 for object 1 is going to be equal to the distance around. So we'll just say distance divided by time, and that distance is the circumference. So that's going to be 2 pi r1 divided by the time interval t, and then V2 is going to be equal to 2 pi r2 divided by t. So the point is that the size of the rolling object will determine what the rotational rate of the object is going to be as we see the object translating through space. So if we look at this as though it were a wheel rolling across the ground, so here's the ground, and now the center of mass of the wheel is moving to the right, so it's going to have a velocity which is to the right. We'll notice a couple of things. One, we're going to notice that at the point of contact right here, that the wheel relative to the ground is not slipping. So there is no slipping. And this is going to imply that the velocity of the wheel with respect to the ground is 0. There's no slipping. It's the center of mass which is moving forward through space. But this one point of contact, there is no motion relative to the ground itself. The velocity for the center of mass is just what we would typically measure as v tangential. And that also means that the speed for the outer edge of the wheel, as it's fixed in space, is also going to be the same as the velocity for the center of mass. So we can say that v tangential is going to be equal to vcm, how fast the center of mass is moving. At the top of the wheel, we've got two things going on. One, it's moving with a velocity of v tangential, which we said was equal to vcm. And so we would put that vector on there like this. That's going to be vcm. But not only that, not only is it rotating, not only does it have that v tangential, it also has vcm being added onto it. So it's going to have an additional vcm. Okay, so let's make sure we label these arrows in a way that you understand. This is v tangential. That's just a natural consequence of the rotation. This vector represented vcm because this entire object is moving through space with the same speed as the center of mass. So when you look at the speed of the top of the wheel with respect to the ground, it's actually moving at 2 vcm, v tangential plus vcm, and so the velocity at the top is equal to 2 vcm, or we could say it's equal to 2 v tangential. All right, now if that was a little confusing, I apologize. We're going to go over that in much more detail in class so that you understand it more fully. It is very difficult to try to do this through the video format, so don't worry, and it's not even a big topic or a huge deal, something that we're going to have to worry about. I point it out because it is a necessary thing for you to know, but it doesn't really have any practical consequences for us in terms of doing physics. You know, there might be an occasional question here or there, but probably not. Now, what is important though, and this is the big thing, this is really what I was wanting to get to today in this video, and that is the bridge equations. The bridge equations are what relates translation and rotation. So the two motions must be related somehow. They must be relatable because of the relationships that we see with this rotating object, this ball which is rolling across the ground. Okay, we know that the center of mass and the outside edge of the wheel must both have the same speed. So we're going to use the bridge equations, and they relate rotation to translation. Now, we're going to start with, believe it or not, just the definition of the radian, but we're going to rearrange it so that our emphasis is not on the angle theta, but the emphasis is going to be on the distance traveled, or what would be the arc length of the circle. So we have S is equal to theta times r. And remember that the radian was defined as theta is equal to S over r. So we just rearrange that. Now, if we change the position or the arc length in some period of time, that means we're also going to be changing the angle which is rotated in the same period of time. So we're going to really have a delta S over delta t is equal to delta theta over delta t times r. Now, you should know what delta theta or delta S over delta t is. That's just going to be velocity. And delta theta over delta t, that's going to be omega. Okay, so it's angular velocity. So our first bridge equation is S equals theta r. The second one is V equals omega r. And then the third one follows from the same logic. If I do delta V over delta t, I'm going to get acceleration, translational acceleration. And if I do omega, delta omega over delta t, I'm going to get angular acceleration. And so I end up with A is equal to alpha r. So these are the three bridge equations, and they are what allow us to connect rotation with translation. This is going to become very important whenever we do, well, with most of what we do in rotation, because a lot of what we do, we're looking at objects which are moving through space. You know, they're rolling or something along those lines. Somehow they're rotating. That very often occurs in real life. And so we've got to be able to relate the rotational piece of it with the fact that we can see that it's translating through space. So let's go ahead and take a look at an example of using the bridge equations. Okay, so go ahead and read the question and give it a try, and then we'll come back and we'll do it together. Okay, welcome back. So let's go ahead and see how you did. We're just talking about a normal bicycle, a mountain bike. It has a 26-inch wheel. All right, so when you look at a bike and they give you the tire size, 26 inches is going to be the diameter of the wheel itself. And so the first thing that we need to do is we need to convert this diameter to metric units. And when you look at our bridge equations, we're looking for the radius, not the diameter. So we have a little bit of converting to do off the very start. We have basically R is going to be equal to 13 inches, and we need to convert that to meters. So in order to convert that, we're going to take the 13 inches and we're going to multiply that by 2.54 centimeters in an inch, and that's going to give us 33 centimeters, which is 0.33 meters. Okay, now we know that the velocity is 4.0 meters per second, and we just want to know how fast is the wheel rotating in radians per second and then revolutions per minute. So for part A, we're going to just relate the velocities. So that's going to be V is equal to omega R, and we're looking for omega because we've been given V. So omega is equal to V over R, which is going to be 4 divided by 0.33. So we get 4 divided by 0.33, and that's 12.12. So omega is equal to 12.12 radians per second. Now to convert 12 radians per second into revolutions per minute, we're going to just do a conversion. Okay, so this is going to be 12.1 radians per second times 60 seconds in 1 minute times 1 revolution over 2 pi radians. And so we can cancel out our radians, we can cancel out the seconds, and now we're left with revolutions per minute. Okay, so this is going to be 12.1 times 60 divided by 2 pi. 12.1 times 60 divided by 2 divided by pi. And that's going to be 115 revolutions per minute. Okay, so part A is done. Now, part B, we're being tasked with determining how many rotations will the wheel make riding 1 kilometer. Well, a kilometer is 1,000 meters, so this is going to be our arc length. S is equal to 1,000 meters, and we can relate the distance traveled using S is equal to theta r. Remember, theta will be in radians, but we're looking for theta. How many revolutions or how many full rotations will it make? So theta is equal to S over R, and S was 1,000 meters. R was 0.33 meters, and so this wheel will make 3,030 radians worth of rotation. And so now all we have to do is convert that to revolutions. And so we get 3,030 radians times 1 revolution over 2 pi radians. Our radians cancel out. So 3,030 divided by 2 pi. And that's going to be 482 rotations. Okay, so in part C, we're being asked to do this again, except this time we're going to be doing it for a much smaller wheel. Okay, so in order to do that, all we have to do is convert the 10-inch radius of the smaller wheel into meters. And so we get R is equal to 10 inches, but we want to convert that to meters, so we're going to multiply that by 2.54 centimeters in 1 inch. And so we get R is equal to 0.254 meters. Okay, so now we're just going to do the same thing that we did before, and we're going to have omega is equal to V over R, and V was equal to 4. R is now equal to 0.254, and so omega becomes 4 times that approximately, or 15.7. That's going to be 15.7 radians per second. And if we want to convert that to RPMs, we just have to multiply it by 30 and divide by pi. So we'll take our value there and we'll multiply it by 30, divide that by pi, and we get 150 RPMs. So there's our answer to part A of part C. And then the answer to part B of part C, it's again going to be the same. So we're going to say theta is equal to 1,000 divided by 0.254. So that's going to be approximately 4,000, but let's see what it comes out to. 1,000 divided by 0.254. That's 3,937. And that's going to be radians. And so all we have to do is now convert that into rotations or revolutions. And so let's see here, 3937 radians times 1 revolution over 2 pi. And so we divide this by 2, and we divide it by pi. And that's 627 rotations.